Today on How It's Made. Dragster tires. Icing. Floating docks. And spiral pipes. A dragster's tires take quite a beating during the brief but fast run down the racetrack. The tires have to face full-on acceleration right out of the starting gate, then heavy-duty braking after the finish line, with the car deploying a rear parachute and slowing to an eventual stop. A drag race is the ultimate automotive sprint, with rapid acceleration to speeds topping 310 miles per hour. Optimal tire traction can give a car the winning edge. Dragster tires, like most tires, are made from rubber, which hasn't been cured to a firm and permanent state. For most parts of the tire, they reinforce the rubber with nylon fabric. The machine heats and kneads rubber slabs until they melt, then coats both sides of the material with a molten rubber. When the fabric-reinforced sheet of rubber cools, the machine slices it into pieces of a specific length, making the cuts at a diagonal called a bias angle. A skilled tire builder then joins the edges of a piece to form a band, sticks it to an identical band made of an opposite bias piece. Layering increases strength, then stretches this two-ply band over a tire building machine. Next, he applies the belts, two opposing bias pieces of fabric-reinforced rubber, which he lays diagonally onto the tread area of the tire. A laser guide marks the edges so that he can match the belts to each other. These belts help give the tire stiffness, strength, and stability. He uses a roller to press out any trapped air between the plies and belts. This helps ensure a thorough bond. After a stitcher wheel folds down the plies, he folds the ends of the material into the machine. Then he applies a contact cement type material to enhance the natural adhesion of uncured rubber. Meanwhile, an automated machine makes the tire's beads, the rigid hoops around both sides of the opening, which holds the tire firmly to the wheel. Each bead is made from a thick steel wire. The machine first encapsulates it in rubber. Then it winds the bead around a mandrel up to 50 times, forming a hoop. The machine forms 4 beads at a time. The next machine wraps the hoop in a piece of fabric-reinforced rubber. This additional layer will stiffen the sidewall, the non-treaded area of the tire. The builder uses a tool called a bead server to mount the finished bead. While the tire is spinning, he applies the contact cement type material to help the rubber-to-rubber adhesion when he wraps the plies around the bead to secure it further. The stitcher wheel smooths the plies flat and pushes out trapped air. Then the tire builder applies a strip of fabric-reinforced rubber on top and rolls it flat. This strip will make the bead area more durable when the tire is mounted on a wheel. He applies a layer of non-reinforced rubber on the sidewall. This covers the edges of the plies and will help the tire retain air once it's inflated. This machine makes the tread by extruding molten rubber through a die into a continuous strip, then applying it onto the spinning tire. The fully constructed tire now goes into a press to cure. Inside, a hot mold closes around the perimeter, while a bag inflates in the middle, pushing the tire outward against the walls of the mold. When the tire comes out about half an hour later, the rubber is no longer soft and pliable, and its chemical structure is stabilized, locking in the final dimensions. Workers seal the wheel opening and inflate the tire to hold the shape until the rubber cools. Once the rubber has cooled to room temperature, which takes about an hour, the tire undergoes a series of quality control checks. Here, a worker performs a visual inspection while trimming off excess rubber from the bead area. Before the decals go on, they also X-ray the tire, looking for any internal flaws. Life in the fast lane, while exciting, is short. Dragster tires need to be replaced every 4 to 6 trips down the drag strip. Icing dates back to 17th century England. Early versions were poured directly onto cake. The cake was then put back in the oven until the topping cooked to an ice-like glaze, hence the term icing. Hundreds of years later, success never tasted sweeter. Today, icing comes ready-made in cans and tubes. No need to make a sticky mess in the kitchen. Just press the nozzle to transform a plain cupcake into an elaborate dessert. It takes a dozen different ingredients to make icing, beginning with vegetable oil shortening. They encapsulate food coloring in the block of shortening. This keeps the food coloring from becoming airborne, as a mixer creams the shortening with sugar, which they pipe directly into the mixer basin. Sugar is the main ingredient in icing. Corn syrup is the next ingredient. It adds more sweetness and liquidity to the mix. The mixer arm spirals around the basin for a few minutes to blend everything. Then they add cornstarch, which will act as a thickening agent. They pour warm water into the mixture and beat until smooth. If the icing consistency is too thin, they thicken it with more sugar. This 1,000-pound batch of icing is done, and there's enough to fill 2,000 aluminum cans. A conveyor delivers the cans to fillers that inject half a pound of icing into each can. The system fills 3,600 cans an hour, and no one has to get their fingers sticky. Plastic nozzles now funnel toward the containers, and with perfect timing, a press seals one to each of the icing-filled cans. At the same time, a pump shoots air into a small hole in the bottom of the can. This pressurizes the icing so it can be pumped out when needed. The burst of air carries a tiny rubber cap with it, and it plugs the hole to maintain the pressure. The cans move forward and meet up with the applicator tips. There are 4 tips per can, held together by little plastic connectors. The 4 applicator clusters fall out of the feeder and land on the can nozzles. Clear caps then fall into place on the cans. A blade cuts a labeled plastic sleeve to the correct length. The sleeve drops onto the cans, draping them loosely for the moment. They ride by a spinning plastic disc that tugs the sleeves all the way down. Then it's into a dryer, where the heat shrinks the wrap to the cans, sealing the icing. It's a perfect fit. Next, they make icing for packaging in squeeze tubes. They blend together the same ingredients, but in different amounts and in a different order. This achieves a thicker consistency. Thicker icing can be more easily squeezed out of tubes. For ready-made icing, it really is all in the packaging. A mechanized arm picks up the squeeze tube and delivers it to the filling machine. A vacuum pump sucks out air and any contaminants. Another mechanism orients the tube for filling. Nozzles now inject thick yellow icing into the tubes, but stop short at a complete fill-up. leaving space for the open ends to be closed and sealed by hot jaws. Once closed, the machine ejects the tubes. Each one contains 4 ounces of icing. It's about half as much as the can. To decorate with icing from a tube, the consumer squeezes it out of the bottom tip. To apply icing from a can, you pump it out of the top. No matter how you ice it, the result will be sweet. The Egyptians built the earliest known docks on the shores of the Red Sea around 2500 BC. More than 4,000 years later, our lakes and rivers are dotted with floating structures where boaters can dock their crafts, go for a dip, or just lounge in the sun. Floating docks can be much more than just walkways where you tie up your boat. They can be waterborne buildings with slips, jet ski ports, and even a rooftop deck. This facility has created its own computer-aided design software. With it, they can quickly design each component of a dock in 3D. The program will even calculate how many floats are needed and where they should be placed to keep the dock level in the water. Thanks to its lightweight, rust-proof strength, aluminum is the ideal material for building docks. All the aluminum here has been extruded in unique shapes according to the design requirements. The plans are printed and workers consult them closely as they cut and form the material. The blades they use are specially designed for cutting aluminum. They use a variety of methods to form the shapes, including drill presses equipped with components called hole saws. Workers lay the material out on the factory floor in preparation for assembling the structure. The final assembly of the floating docks will happen on the water at the site. They tack weld the parts to each other, then make sure everything is perfectly square before doing the final weld. Unlike steel, aluminum loses strength when it's welded. For this reason, the designers of these docks have created special aluminum sleeves for every major joint. That means there's extra metal supporting the weld and strengthening the structure. To make sure everything fits properly, the workers join the sections to each other with stainless steel bolts and lock nuts. There is minimal reaction between the different metals because there's so little stainless steel relative to the quantity of aluminum being used. Once the bottom section of the dock is assembled, workers build up from there. For this test phase, they use shortened temporary roof poles to make the process easier. The blue material on the poles is polyethylene bushing, which prevents creaking when the dock is stressed in turbulent water. Because aluminum is so lightweight, there's no need for cranes in an aluminum dock facility. Manpower is enough. Workers attach a series of narrow aluminum tubes called purlins to the roof and deck. Workers install the roofing by screwing it into the purlins. In most cases, the roof won't be installed until the dock is assembled on site. Satisfied that everything assembles correctly, the workers take it all apart. They flip the lower sections over and attach the floats. These floats consist of roto-molded polyethylene shells. Styrofoam has been expanded in place to fit inside the shell perfectly. Even if the outer shell breaks, the dock will still float. This facility offers a range of decking options from aluminum to concrete to plastic composite to specialty woods like this one, which is called Ipe. Like teak, Ipe is incredibly durable and extremely stable. In other words, it won't rot, swell, or contract, despite extended exposure to a high humidity environment. If the dock has an upper deck, it needs a railing. It's important to have something to lean against when you're sipping cocktails and watching the sunset after a long boat ride. Of course, it's also a crucial safety feature. There are 12 different components to assemble for just this one section, and there might be as many as 15 different sections of varying lengths for an entire dock. Customers can choose to add a range of accessories to floating docks made at this facility. To make things like safety railings and ladders, workers use a hydraulic bending machine to shape aluminum tubing to the required contours. All the aluminum these manufacturers use in their floating docks is a marine-grade alloy especially resistant to degradation when exposed to water. Finally, it's time to build the docks in place. Thanks to careful planning on the part of the manufacturers, assembly is a breeze. The crew doesn't need much more than a ratchet set to pull it all together. It's smooth sailing from here on out. In the modern world, steel pipes form an underground network to deliver necessities like drinking water or fuel. These pipes are often spirally welded and can be made in any size. In fact, longer pipe means fewer joints and less work to install them underground. Spirally welded pipes can be short, or they can go on and on. The potential length is limitless because, unlike other kinds of pipes, spiral pipes don't have to conform to the size of a forming roll or the dimensions of a steel plate. They can spiral weld these coils of steel sheets endlessly. But first, they have to take the kink out of the coiled steel. A machine unwinds it and pushes it between rollers to completely flatten it. A fixed arm then presses the steel against rollers to round it to a precise diameter. And an automated system welds the formed pipe from the inside. A barely visible mantle of powdered flux protects the welding process. Copper-coated steel wire acts as both an electrode for the welding process and as filler material. With the inside weld complete, a second welder device works on the outside of the pipe to give it a double welded seam. A plasma torch cuts the pipe to length cleanly by melting it. In this case, they're making a water pipe that's 6 feet in diameter and 50 feet in length. The pipe then rolls over to the next station. Here, a worker grinds both ends of the pipe to improve the profile. Then it's over to a die. It stretches one end of the pipe to create a slight flare or bell. This will allow it to be connected to the narrower end of another pipe, forming what's known as a lap joint. Next, they cap the ends of the pipe and pump in water to a highly pressurized state. They look for leaks in the weld and confirm that it's watertight. Another worker installs rubber dams at both ends of the pipe. A cement fixture then flows into a long applicator with a nozzle. The nozzle applies the cement to the pipe's inner wall as the pipe spins and generates a centrifugal effect that's 70 times the force of gravity. This causes the cement to be distributed uniformly. The rubber dams contain the cement during this process. The spinning displaces water in the cement, and a blower forces that water out of the pipe. Next, a worker drapes plastic onto both ends of the pipe. He tacks it with magnets and then secures it tightly with an elastic cord. He pumps hot steam into the pipe. Over a period of 18 hours, the steam cures the cement. It's a slow cure for better structural integrity. For our camera, they open one end of the pipe for an inside look at the steaming action. 18 hours later, they remove the rubber dams. The spiral welded pipe now has a tough protective inner liner. Next, the pipe moves into a blast chamber where fine steel shot bombards the outside of the pipe to clean it thoroughly. This prepares it for the next step. A sprayer applies a liquid adhesive. Over the adhesive, they wrap a polyethylene-backed tape. They apply a total of 3 layers of tape. The first one provides corrosion protection to the spirally welded steel. The other 2 layers protect the first. They give the spirally welded pipe a tough outer skin. The 3 tapes are color-coded. This will allow the depth of any damage to be quickly assessed on site. They produce approximately 15 spirally welded water pipes per 8-hour shift at this factory. They should last for a century underground. If you have any comments about the show, or you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.